So similar to L1 and L2 regularization of our linear regression or logistic regression, we have L1, L2 regulation in L1 or L2 regularization similarly exist in neural networks also. Apart from that, there is one more regularization technique that is called dropout layers. Dropout. So randomly we switch off weights of some neurons. Means weight will be 0 means that neuron will disappear, right? If weight is 0 means that neuron is not satisfied. So randomly we switch off some neurons. Means we reduce the number of neurons practically. We switch off some neurons and then we do regularization.
But initially, do we need to take all the input variables or
no, when we come to practical problems, we will learn that when we design neural network, in the design itself, we put some dropout. Okay. Say 0.2, 0.3% dropout we put in the design itself. And then the dropout percentage fraction also becomes a hyperparameter. That dropout value should be 0.2, 0.3, whatever it should be. So that is also becomes a hyperparameter.
Okay, because why I am asking, because in regression we are considering all the parameters initially and then we are dropping out, right? So here we are doing initially itself.
No, you design, it is up to you. Na? If as a neural network engineer, if you don't want to put dropout layer, you take all.
Okay.
If you think that function is overfitting, then you put some dropout, right?
Okay. Yeah, but it will cost. Yeah, that is right.
Yeah. Okay. So randomly we are. So this is a very standard technique and very easy to add dropout in. After each layer, you have to add one line of code, dropout, and then you have to specify fraction how much, 0.2, 0.8, 0.2 means more dropout, 0.8 means less dropout. Okay. Very easy to add actually. After each layer, you have to add one line of code to add the dropout. We will learn it, okay?
Okay.
So now going ahead, then I want to show you one feed forward. See, back propagation example also I have here. If you can see my screen, I have a back propagation. Example also, but I'm not going to cover it today's class. Sometime later, when you become gain some level of mastery in neural networks, that time we'll take up back propagation. Right now, we'll understand only forward propagation, feed forward. Okay. So I have some article here with feed forward. I want to explain you. It only now numericals. Okay. So you will very easily understand. So now you see here. It is a simple perceptron. Let us first work with a single unit. It is a perceptron, our yesterday's perceptron. X1 and X2 are two input variables. X1 is input, X2 is input. Weight W1, W2 associated with one each input. Then you have Z and then you have bias. Okay. Then second means in this neuron, what you do once you calculate Z means output of that. On that output, you put activation function. Then you get the final output. So what is how the equation becomes? Z is nothing but your X1 W1, X2 W2 plus B. We saw it yesterday. Very simple. X1 W1 plus X2 W2 plus add one bias. Why add one bias? There is one neuron, one bias. Now we apply a softmax. We apply a activation function. So what does it mean? Here we are applying a softmax. Sorry, a sigmoid we are applying. So we are choosing sigmoid as our activation function. What does sigmoid mean? So Z is there, Z is this equation. So sigmoid means everything 1 over 1 plus exponential minus Z, e to the power minus Z. This is nothing but a sigmoid function of logistic regression. So if we calculate this equation, we calculate Z with the help of W1, X1, W2, X2 plus bias, raise it to the power exponential e to the power minus Z, and put in this equation, you get the final output of that neuron. You get the final output of that neuron. Very easy. Understood? So this is what is. This is our Z is nothing but your W1 X1, W2 X2 plus B. On that Z, you apply a sigma means you apply activation function. So it looks like this right hand side equation, this equation. So I'm making it a big. So we make it bigger. This is the equation. Now it is done very easily with the help of numerics. So you will understand more x1 is x1 x2, yeah. So now it is divided. You see this table, it is divided into two parts. One is inputs. X1 and x2 are two inputs. So x1 is 0.1, x2 is 0.2, 0.3. First row you see x1 is 0.1, x2 is 0.3. W1 is 0.6 and W2 is 0.2. So we first determine Z. How would and we are assuming that bias is zero. We are assuming that bias is zero. That is what is our assumption here, just for simplification. So what Z becomes? W1x1 plus W2x2. This equation is this equation. First equation, Z equation. We got 0.12 minus 0.12 we got. Then we are applying activation function. So activation function means what? So 0.12 we got Z we got as 0.12. We put in this equation 1 upon 1 plus e to the power minus 0.12. We get 0.53. So 0.53 is nothing but our output probability. So this is a single neuron, right? So 0.53 is nothing but output of this neuron. So it is a sigmoid function we have applied. So we can say that it is a probability. Otherwise, it is some other function, means it can be any other function, Rayleigh or state function or square. It can be anything. But here we have put sigmoid. So sigmoid we have put, so it is very easily. Similarly, we have done for row 2 and 3. Anybody, any problem here? Any concern here? Any concern here? Raise their hands or ask questions, please. Ashwini, understood?
Yes, sir.
Okay, anybody? Anyone, any problem? Okay, so now let us go a little complex. We have a figure. Figure is always represented a matrix of numbers. So it's an image. So it's 4 pixels by 3 pixels. 4 pixels means 4 rows, and 3 pixels means 3 columns. So it is, there are 4 by 12, 4 by 3, 12 cells will be there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 cells are there. This is nothing but, this is how image is represented. So when we do convolution neural network, that time we'll see how images are represented with the help of a matrix like this. But right now you assume it is an input. So in input we have a square, we have a rectangle of 12 cells. So we give each one of these each one of these 12 as a one input. We straighthen it 1 to 12. So 1 comes here, 2 comes to second neuron, and 12 goes to R12. So we have 12 neurons in the input layer. Sorry, 12 neurons in the input layer. Understood how 12 neurons? Because there are 12 cells in the input figure. So 12 neurons are there in the input layer. Each cell 1 neuron. Okay, each pixel 1 neuron. Then layer 2, we have a hidden layer in which we have 3 neurons. So each one of, if we see operations only for the first neuron of the hidden layer, it is connected with all the neurons. It is connected. So how the calculation go? You see here. So x1 equal to 1, x2 equal to 2, x2 equal to 0, x4 equal to 0. So like that we have x3, x1, x2, x3. So then put it. Okay, so got it. So these are cell numbers actually. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. These are cell numbering. So each of the cells are having these values. First cell is 1, second cell is 2, 1, third cell is 0, fourth 0, fifth 1, sixth 0. Like that we have cell values from 1 to 12. So
based on the grayscale, this one, sir, it's a picture, I guess. So I think it's based on the grayscale.
right?
Yeah, it is
Either
grayscale.
shaded or not shaded types.
Yeah, shaded or not shaded. That's why. But we better not go into that detail because that all we'll see in the CNN anyway. So let us assume that these 12 cells, the 12 values we have, 12 values of input we have, some are 0, some are 1. Okay. Then all 12 inputs are given and we are showing only one neuron of layer 2, first neuron. So let us see how it is then. There are how many weights are there for one? There are 12 weights. 12 weights means how? The W2 means W2 means weights between first hidden layer and input layer. So W11, W12, W13, like W14, W15, W16, W17, 1. It means this first neuron of input layer, first input layer, first neuron, X1. First input layer, layer 1 input layer, first neuron is connected to around we have 12 weights corresponding to that. So 12 weights, so these 12 weights are given here. Then what is the each weight is multiplied by the, see here, each weight is multiplied by the input here, x1 to x2 like this, and these calculations are done. Z has come, and then we have put a activation function on the top of that, 1 plus e to the power minus I z, and similarly we have got the value of 0.7812. So now I want to check one thing here. These 12 weights, how is counting it as 12 weights? Anyone wants to attempt it?
So 12 pixels, so 12 weights for each neuron. When you have 3 neurons in the hidden layer, totally you will be having some 36 weights, 12 into 3.
12 into 3, but how is representing this W11 and W13? So, see, W11 is first is connecting with first, that is W11.
Yeah.
Okay. Then second neuron of input layer is connecting with layer 1, first neuron of the layer 2. So that is representing by W12. And the 12th neuron of hidden layer is connecting with first neuron of hidden layer. So is calling it W112. So W1 means first neuron of the hidden layer. First neuron of the hidden layer. And after that we are counting the previous layer neurons. Understood? No? W11 means W112, it is very clear, right? W1 means first neuron of hidden layer is connected to the 12th neuron of input layer, previous layer. So that is how he has taken W11, W2, and why is summing up all? Because this particular neuron in a dense layer, this particular neuron 1 of layer 2 will get input from each one of the 12 neurons of the layer 1. Understood? Now there will be 12 inputs to this. So can anyone tell why there are 12 inputs to this? Anyone wants to attempt it? Why there are 12 inputs to layer 2? First neuron of layer 2. Why there are 12 inputs?
Because of the 12 pixels, right?
Yeah, because of 12 pixels, right? So input layer we have 12 pixels. So from each pixel there is a input to the first layer of the first neuron of hidden layer. First layer 2 first neuron. Layer 2 first neuron is having input from each of the pixels, right? So that is what is W11. That's why and each connection is having one weight corresponding to it. Each connection is having weight corresponding to it. So for these weights, 12 weights, and plus one bias we are adding, second layer, one bias, B21, one bias we are adding. And when we are multiplying, we are getting Z. We are multiplying everything, getting Z. And then once we get Z as 1.227, that Z we keep in our simple activation function, sigma 2. Activation function we put, we get a value of 0.782. Is this understood by everybody?
So just the notations, I think, is little confusing because I
no, madam. If you
W12,
little bit first thought, I was also confused. But if you little bit remember it, see what he is doing. W1, super subscript you see, subscript only is confusing, right? So
Yes.
W1,
Yeah.
W1 means first neuron of the current layer. So first neuron of L2. First neuron of L2 is connected to the first neuron of
Okay.
L1.
I thought it was the other way around. That's why.
No, no, that's why I was confused, but here it is other way around. Now here, W112 means first neuron of layer 2 is connected to the 12 neuron of L1. Understood, madam?
Yes, sir. Yes, sir. Yeah.
So we are concerned right now only with the only one neuron of the layer 2. First neuron we are taking. First neuron will have 12 inputs from 12 neurons of the previous layer, which is L1. 12 inputs. Each input will have a weight associated with it. A weight associated with it. So weight it will have, and weights, all the values of 12 weights are given, and every neuron has one bias. So bias we are taking at 0. And when we do W1x1 plus W2x2 like that equation, if we do 12 times plus add a bias, we get the value of Z. Once we get the value of Z, we take the activation function. Activation function is nothing but a simple sigmoid. Sigmoid we put and we get the output of this. So H1 is what? H1 is 0.782. H1 is nothing but 0.782. Is it understood by everybody? Ashwini?
Yes.
मैडम सिर्फ यस मत बोलो, समझ में नहीं आया है तो पूछो.
No, sir. It's understood.
समझ में आया आपके?
Yes.
Soman, is it clear to you?
Yes, sir. It's clear.
Himanshu is there? Today Himanshu is not there. So Shailesh, is it understood?
Yes, yes, it is very clear.
So see, this is nothing but for one neuron. Similarly, you have to do for 3 neurons of the hidden layer, because there are 3 neurons in the hidden layer. You see, here there are 3 neurons. Once you do this, you make it as a vector and then take it to the last layer. Same thing again. But this time, sigma 3 means, which is the activation function of last layer, may change. But since it is a single layer, a single neuron here, that also will be sigmoid only, because it is a single class problem. Single class problem means it will be output will be. So this is how feed forward goes. If you see the equations, it is very complex. But if you run with numbers, it is very simple. Very, very simple maths. So this activation function sigma, we have taken it as a sigmoid. It can be any other activation function also. It can be any other mathematical function. So right now we are taking it as sigmoid equation, but it can be any other mathematical equation. There are a lot of choices available, hyperbolic tangent, or it can be a linear equation or whatever. There are Rayleigh, leaky Rayleigh, lot of mathematical functions are available which can be used, and depending upon the function, the output will change. So here H1 is 0.782. So like that, we'll have 3 outputs from the 3 neurons of this particular. 3 outputs will be there from this L2 layer, and 3 outputs will become an input to the last layer, out layer single neuron. And the last layer will give you the final probability, Y. So that's how your neural network works. It is very damn simple, and only equations only look tough actually. But in practice, if you work with numbers, it is really simple. Now back propagation. So back propagation, I just want to show you how it looks like, but I will not go into detail because it's a very complex, not very complex, but you see back propagation. Oh, so I have to open it in. Incognito mode. I will just show you how it looks like. We'll not go into detail. So we go to incognito mode and it opens for us. Then you see what happens. Something else is opened. Yeah. So it opens for us. It's a very nice article. And what is a neural network, input, everything is explained. And some nice figures also given. So weights, biases, hidden layer. So he has created a neural network with the help of Python, which you can see here. Same equation, activation function. And then he has created the final output. Yes. Then feed forward. Feed forward you understand now because we have done with the help of numericals. Then loss is calculated this way. See, when we do the back propagation, we first calculate loss. So sigma of for each data point from 1 to n, for each data point, we calculate actual output minus the predicted output, a square. And then we differentiate it with the help of each weight and bias. So these loss looks like this. And then we differentiate loss with the help of weight. So weight, this weight W is nothing but a vector. So here it is a differentiation with the help of with respect to a vector. Then from that's where it then we are doing some chain rule actually. Chain rule we learn in 12th class. So that chain rule is doing, and then after that he has explained with some numericals. And this is the graph we plot. This is the graph I wanted to show you. See loss. So number of iterations we are going on increasing from 100 to 100 to 1500. Loss. So loss is what? Loss is nothing but this is loss. This is loss. Actual minus predicted square. This we do in actual minus predicted square for all the rows in your data set. For all your data point, actual minus predicted, we calculate the error, we do it square. That is called loss. Okay. So we do it in linear regression also. Same thing is done here. And the plotted loss versus number of iterations. You see now, say after 400 iterations, the line has become parallel to x-axis. So that means from 400 iterations till 1500 iteration, there is no reduction in loss. There is no, we want to minimize the loss, right? We always minimize minimize. What is loss? Loss is the difference between actual values minus predicted values. So we always want actual value to be equal to predicted value. So loss, ideally we want loss is 0, but 0 is not practical. So we want to minimize it. So see, from first iteration till 300 iteration, there is a steep decrease in loss, steep decrease. After 400 iterations, this line becomes parallel to x-axis, means convergence has occurred. Means that neural network, this neural network doesn't need any training beyond 400 iterations. Maximum training, the maximum iterations that we need for this, the convergence of this neural network is 400 iterations. After that, even if you do more iterations, the loss is not going to improve. Loss is not going to improve means the training of your neural network is complete. Is this understood? So this is a nice, with the help of numericals he has explained, and with Python he has done the loss. Everything he has done with the help of Python only. See, loss he has calculated, differentiation and all he has done with the help of Python. If somebody wants to learn it, I'll anyway share this PPT. So I'm not going into detail because I don't think it is required in this class. So I'm not going into detail, but you can go through this example if you want. Okay. So now we come next simple thing. Now I will tell you how to calculate the trainable parameters of a neural network. How to calculate the trainable parameters of a neural network. Okay. So left hand side you see we have a simple neural network with 3 inputs. You see green ones, 3 inputs. We have one hidden layer with 4 neurons, blue ones. Then we have two neurons in the output layer. Okay. So now I told you here he has put one bias in. He has put. Now I told you we add one bias per neuron. One bias per neuron we add. And how many? So how many weights? How many weights will be there? Other than Malini madam, somebody has to tell. Malini madam, you please don't tell. So how many total number of weights will be there? First hidden layer and input layer. How many number of weights will be there, Ashwini?
So 12.
Why 12?
So input layer into hidden layer.
Yeah, 12 weights. How many will be between output layer and hidden layer? Output layer there are 2 neurons, and hidden layer there are 4 neurons. How many weights will be there? You apply same logic, madam.
So 8.
8 neurons, right? Now, how many total biases will be there in this network? Input layer, we don't put any bias, okay? Input layer only input. So how many total bias you can see in this network?
So 2.
No, madam. Just look, see in figure everything is given. Just have a close look. In figure everything is given. Just have a close look. How many total number of biases are there? Anybody else? How many total number of biases are there in this neural network?
6 biases.
Yeah, 6 biases. Correct, madam. How 6? Can you explain, please?
Like as we know, input layer won't be having any bias. We have a bias with each hidden layer, that is blue color 1, 2, 3, 4, and also biases to the output layer. This one.
2 bias, yeah.
green color.
So now how many total number of parameters
4
will be
plus
there?
2.
How many total number of parameters will be there in this neural network?
Like 6 biases plus 12 weights in first thing and 8 weights in second thing.
So total how much?
Addition of all these. 12 plus 8, 20 plus 6, 26.
So you got the answer 26 here, madam, right? You learned it. So you now you see how to calculate weights and see first. How do you see here calculation? How? First, between first hidden layer and input layer, there are 12 weights, 4 into 3. First 12 weights. Plus 4 we have done, you see here summing up all, then we have done plus 4. Plus 4, why we have done 4 biases of hidden layer, plus 4. Okay, that is done. Then you go forward. Then we have plus 4 into 2. Don't get confused by this. How is done? 3 into 4 plus 4 plus 4 plus 4 plus 4 into 2. Yeah, plus 3 into 4. 3 into 4 is for between. These are weights first he has calculated. 3 into 4 in between first two layers, and 4 into 2 in between the next 2 layers. Then he has added
4 into 2 is 4 in, yes, 4
into 2, yeah, right. So then he has added 1 into 4 bias for first and then 1 into bias for second. So total 20 weights and 6 biases, 26 like this. So if neural network is bigger, your number will be bigger, but calculation formula will remain the same. Understand? No? It is very simple, right? So these neural networks, in technical terms, this neural network is having 26 trainable parameters. 26 trainable parameters. Why 26 trainable parameters? Because during our iterations, during our feedback, during our backward pass, we have to update our weights and biases, which are 26 in numbers. So we have to finalize 20 weights and 6 biases. So that is how we calculate the total number of parameter in a neural network. Very simple. I done for a simple neural network. If network is bigger, your number will become bigger, but formulas will remain the same, concept will remain the same. So anyway, this also computer does for you. Then this also not needed. Now I think we have come almost to the end. Then you see what is the relation between this slide is courtesy Andrew Ng. Anybody heard the name of Andrew Ng?
Yes, sir. Deep learning.ai.
Deep learning.ai, right?
Yeah.
So he is one of the best known scientists in the world for deep learning. One of the best known. First, he used to be the Chinese guy. He used to work with Google first. And then after Google, he has shifted to one Chinese company. So now he's working for a Chinese company. And I think he's founder of deep learning.ai. So he is one of the best known scientists for deep learning. He is the one. And from his book, I have taken this particular graph. So can anybody interpret this graph? For me, Malini Madam, can you interpret this graph for us?
Yes, sir. As the amount of data is more, the performance is high. For very small training data sets, the performance is not great, as you can see somewhere in between.
Yeah.
For very large neural networks, that means very complex neural networks with more layers and hidden layers and more neurons and all, the performance is very high. For
Performance is very high.
high.
But one thing you are missing, madam. One important thing you are missing. So, madam has told two things. Let us tell the below line, the bottommost line you take.
The red line.
The red line.
The traditional learning algorithms.
Yeah.
No matter how much amount of data you give beyond a point, it remains the same, the performance.
Performance remains the same. But one more point is missing here. If the complexity of your neural network increases, the amount of training data you require to training also increases.
Yes.
See, if you yellow one, you see small neural network. So small neural network, even if we are increasing data, but performance line has become parallel to x-axis, means there is no improvement in performance. Performance has become constant for a certain amount of data. Medium neural network, then my line is becoming still flat, but it is becoming flat after a yellow line. But my neural network is big. I am giving heavy amount of data, but still performance is going on improving. Means if I do a very complex neural network, I need huge amount of data to get a optimum performance out of it, to train it. Understood, na? So neural networks are always resource hungry. They need large amount of data to train. They need very large computational resources to train. They need very big GPUs, lot many hours, sometimes months together we keep on training. So these kind of very complex neural network we can never train at home or in any laboratory. These kind of very large complex neural networks are there with thousands of layers in between, or some hundreds of layers in between, hidden layers, and millions of trainable parameters. Such neural networks have been trained by companies like Google and Microsoft. Okay, so why they are able to do that? Because their resources are infinite. They have infinite number of GPUs. They have infinite number of computing available to them to train these machines. And on such machines also, trainings was going for weeks together. One model they have given for training, millions of parameters, and that will run for a few weeks. Training will happen continuously. Then only that particular neural network will get trained. So that kind of neural network also have been developed by Google and Microsoft of the world. So whatever we will do in our class, they will require around 30 minutes to 45 minutes to train. 30 minutes to 45 minutes they will require to train, and that too on Google Colab Pro. And same neural network, if you train on your home PC, it may take 10 hours, 20 hours. But same if you do on Google Colab Pro basic version, then maybe 30 minutes, 45 minutes, it will get trained. So that is what we are going to do in the class. Okay, beyond that we cannot go. So Udesh, is it understood? Udesh Saman, are there in the class? Okay. So I want to tell you this softmax sigmoid. You see for sigmoid function, I want to just tell the equation. Equation is very simple: 1 upon 1 plus e to the power minus 6. What is softmax? Softmax I told we use in output layer when we have multi-class problem. See the equation. Equation is simple. E1 upon, suppose we have 3 classes. Suppose we have 3 classes, then it will be E1 e to Ez upon Ez1, Ez2, Ez3. Like that 3 it will be there. Then E2 upon E1, E2, E3. Then E3 upon E1, E2, E3. Like that 3 probabilities will be there. So that is what softmax for multi-probability. Is this equation understood? Or are you worried by sigma actually? So first of all, we have e to the power z. Z is nothing but the output of the neuron. And it is not the output, but it is this softmax is the activation function. Now it applies on z. So we have seen backside what is z, right? So z is nothing but, I want to show you. Z is what is there in the bracket. Sigma you see the second last layer, second last equation. Sigma is the activation function. Inside bracket we have W1 H, W into H plus B. This is nothing but Z. This is nothing but Z. This is nothing but Z. Then we are applying sigma here. Sigma is nothing but softmax or sigmoid. So here we are applying softmax function. Softmax function. So like that we have multi-class problem. We do this softmax. So it is E1 upon, if there are three classes, E1 upon E1, E2, E3. Then E2 upon E1 plus E2 plus E3. And third will be E3 upon E2 plus E1 plus E2 plus E3. And sigmoid means only one, E1 upon E to the power minus x. I just wanted to show you the equation. Then activation functions and how to choose. First of all, I want to tell you here that why we need complex decision boundaries. Like why we need activation function. Activation function, as I said, can be multiple types. And generally we choose a non-linear activation function. We don't choose a linear activation function. What is linear? In the three graphs which are showing here in the middle, in middle there are three graphs here I am showing. So Ashwini, which one of that is linear and which is non-linear?
So first and second are linear.
Yeah. And third is non-linear, right? So now again, my next question to you, Ashwini. Why we have made third graph as non-linear? Any idea? If you, yeah, why? Tell me, madam, why we have made it non-linear?
So no idea.
No idea. I tell you why. See, in third equation you see where it is non-linear. The dots are separated. The dots cannot be separated by a single line, straight line. To separate the red dot and blue dot, we have to put a curve line only. Curve line only can separate them, right?
Yes, sir.
That's why we have made this separating line, which is curve or straight line. This is called a decision boundary.
Okay.
So we have some classification type of problems in which yes and no or class 0 and class 1 cannot be separated by straight lines. We have like this, you see on the right hand side decision boundary of these five red balls and blue plus, they are separated by a very complex figure, right? So we have this kind of decision boundaries sometime. See, there are two classes here. One is red. See the rightmost. There we have two type of classes. One is red and one is blue, right?
Yes.
They can be separated, but they cannot be separated by a straight line or any curve also cannot separate. To separate them, we have to make a complex closed form curve, right?
Yes.
So this closed form of this is called decision boundary, which is separating fraud transactions from non-fraud transactions. Fraud transaction means red, non means blue. Non-fraud transaction means blue. So we are separating some fraud transaction with not fraud transaction by this kind of boundary, which is very complex. So to get this kind of complex type of decision boundaries, or this in middle you see below we have curve. So this curvilinear type of decision boundaries, we need non-linear activation functions. We need non-linear activation function. If we apply linear regression, this kind of curve or this kind of complex boundary we can never get. And we use neural networks because we need non-linear relationship between y and x, because relationship between y and x in our data set is so complex that we need a very complex non-linear function. We want to introduce non-linearity in our model. So how we introduce non-linearity in our model? We introduce this non-linearity in model by the use of activation function. Now tell me, madam, anybody wants to tell whether this softmax and sigmoid are linear or non-linear? Softmax is
non-linear.
Softmax is non-linear, right? Sigmoid is non-linear. And what about softmax?
Softmax is also non-linear.
Non-linear. Okay. So now linear function sigmoid I can show you on the 2D graph. Okay. See, suppose I have 4 class problem. There are my problem I have 4 classes, which I have to separate 4 different type of classes in the problem data. I have to separate data into 4 classes, 1, 2, 3, 4. Then I will use sigmoid problem, softmax, right? So can I represent 4 class sigmoid? 4 class software function can I represent on 2D paper or 3D paper, 3D diagram or 2D diagram? Can I represent it? I have 4 classes. Okay. So my dimensions of my softmax function will be in 4 dimensions. So that kind of softmax function I cannot show using either 2D diagram or a 3D diagram. When I plot a softmax function with only 2 classes, it is same as a sigmoid function. Sigmoid and softmax become the same. When only for 2 classes 0 and 1, softmax and sigmoid are same, they can be plotted in a 2D curve. But when classes become more than 3, softmax function dimensionality increases from 4 to 5 to 6. So at the time softmax function will become multi-dimensional. So it cannot be plotted. So now, having said that, I want to show you some activation functions, and that will be the end of our lecture today. So some activation functions. This also will be shared with you. So we have this gentleman Jason Brownlee. He writes very nice article about machine learning and deep learning. See, so this function, can anybody recognize what this kind of, which is this function? What is the characteristics of this function? This is called ReLU, R-E-L-U. R-E-L-U it is called. So what is the character? Can somebody read this? Malini madam, can you read this function, how it is behaving?
Beyond for all negative values, it is of x, it is 0.
Yeah.
And, for positive values of x, it is showing a linear kind of trend.
Okay, very nice, madam. So this is nothing but our ReLU function. So ReLU function means for any negative value, the output of ReLU function will be 0. And for any positive value which is greater than 0, the output will remain the same. So equation you see is like this. Where is it equation? Equation of ReLU. Okay. ReLU equation is not given here. I want to show you ReLU equation. So ReLU equation I will show you. This is a ReLU function. Then ReLU function. I have not shown it properly. See, this is how they are showing ReLU function, but there is a better representation of ReLU function. I can see that there is a better representation which I am not getting here. So it is understood what ReLU function is, but wait a minute, we'll see better. It's here better. I want to show you in a better form. Yeah, here it is. This is what I wanted to show. See here, ReLU function. Fx is, suppose fx is a ReLU function. How is it? ReLU is nothing but for any value of x less than 0, it is 0. For any value of x greater than 0, it is the same. Understood? Is this understood? Very simple it is. For any value of x less than 0, it is 0. Any negative value also, it is 0. For any value greater than equal to 0, it is same thing. Same equation, x equation. Is it understood? Ashwini, is it understood ReLU function?
Yes, sir, understood.
Understood, na? So it is very simple. ReLU function understood. The next function I want to tell you, sigmoid. So sigmoid looks like this, madam. Sigmoid I already showed you. Sigmoid equation I will show you again. Sigmoid is this is sigmoid 1 upon e to the power minus x. So how it looks like sigmoid? Sigmoid looks like this. Minimum value is 0 and the maximum value is 1. And in between we have a S curve. S curve we have. So in between, it is always varying between 0 and 1. And in between we have probability values set 2.2, 0.3, 0.4, 0.6 like that we have. So it is very close to the step function, but it is not a step function. It is slightly distorted step function. Okay, so then we have 10H. 10H, how it looks like? 10H is also looks similar. See, you remember this Rayleigh curve? So similar curve is there for 10H also. 10H also has a similar curve, but it varies from -1 and 1. Rayleigh was sigmoid was varying between 0 and 1. 10H is varying from -1 and 1. That is 10H. Equation of 10H, if I want to show you equation of 10H. Equation of 10H, again I have to go to Google Cloud only. Equation of 10H.
It is there, sir. It is there in the page.
Where? This one?
Yeah.
It's not very clear now, madam. I want more clear representation. 10H. That is not very clearly written, no? It is there. 10H function. If you go to Google Cloud, everything is there, madam. Okay, very first we got it. So this is what 10H. See, 10H is this. So see, this is 10H. E to the power x minus e to the power minus x and sigma e to the power x plus upon e to the power minus x. It is very simple 10H equation. So this is 10H and this is sigmoid. This is sigmoid. This is sigmoid. If one class is 0 and one class is 1, then 10H, okay, let us not get into that. So this is 10H and this is sigmoid. Understood? So this is how it is. Then we see the next activation function. This is 10H. Yeah, 10H varies between -1 and 1. Then there are only 3 functions given here. So 3 main functions. One function is our one activation function is Rayleigh. Rayleigh I shown you. Rayleigh this function. Then sigmoid, this function between 0 and 1. And 10H, which is -1 and 1. So how to choose an active? So now I wanted to tell somebody to tell why we choose, why we need an activation function. I have explained it, but I want somebody to tell why we need an activation function. Why we need an activation function? Can somebody wants to repeat it? It's the end of our class actually. So why we need an activation function? Can anybody attempt it? Malini madam, you or anybody, Shailesh, anybody? Why we need activation function?
Sir, it's mainly because we finally want to arrive at probabilities of a particular class. So an activation function like a sigmoid can give me a value between 0 and 1.
No, madam, that is, you have told, that is true about only for output layer you have told. I will ask you next question. Why I put activation function in the hidden layer? Output you have told correctly because I want values between 0 and 1. Sigmoid gives me that. Sigmoid and softmax both give me values between 0 and 1. Sigmoid gives me for 2 class problem. And if there is a multi-class problem more than 2, 3, 4, 5 classes, then I use softmax. So both give me value between 0 and 1. Okay, fair enough. But that is for output layer. Why I put activation function in every neuron of the hidden layer also. So my question is that why we put activation function in every neuron of the hidden layer? Why activation function is needed?
Because there is a non-linear boundaries between the decision class.
That is okay, but still you can explain in a better way. It is written in front of you here. Non-linearity is needed in activation function because the aim in the neural network is to produce a non-linear decision boundaries via non-linear combinations of weights and inputs. So we want to have a non-linear combination of weighted bias, non-linear combination we want to have. So we don't want straight line relationship between, we don't want a straight line relationship between our weights and biases. We want a non-linear because we want to have complex decision boundary. Our problems are so complex, a simple linear line cannot represent it. So we want non-linearity. Non-linearity between what? Non-linearity between weights and biases. How to introduce that non-linearity? That is by putting activation function, non-linear activation function in. A non-linear activation function we put in every neuron of the every hidden layer. So now my last question for today. In this particular, is this a linear function or a non-linear function? Is this a linear function or a non-linear function? This is a linear function or non-linear? Anyone? Rayleigh. Is it linear or non-linear?
Sir, it is linear.
Non-linear.
No way it is linear. It is non-linear function. If it is linear, means it is only will be a straight line. See, I will tell you what is linear function. It is not a linear, non-linear function. See, I will tell you what linear function is. Then you will realize the difference.
Infinity to 0. It is
No. See, linear function. Linear function you want. So these are all linear functions. This is a linear function. Linear function. Okay. So these are two equations of two linear functions. Two linear. Blue is one linear function and red is another linear function. So equation of a linear function is always a straight line. But you see, Likhi Rayleigh. So let's see the Rayleigh. Rayleigh is first parallel to x-axis and then it becomes a linear function. So it is divided into two parts. Less than 0 also it is a linear function, but it is parallel to x-axis. More than 0, it is another linear function. So overall, it is a non-linear function, right? It is not a straight line. Rayleigh function means you have to consider the horizontal line also and the slant line also. Together will form a Rayleigh function. So Rayleigh function is a non-linear function. Understood, na? Understood, Shalja madam? Hello? Hello? Am I audible?
Yes, sir, you're audible.
So is it understood why it is a non-linear function?
Yes, sir.
Where madam, where other madam has gone? Udesh, is it understood?
I'm
Yes,
not
sir.
sure Shailaja has joined.
Then some lady was speaking, na, just now.
That
One
was
lady.
Shrutika.
Yeah, Shrutika madam
It
understood.
was me, sir. Yeah.
Yeah, madam.
Yeah,
no,
I
madam,
already said non-linear, sir. Yeah.
No, somebody told, I think your voice was different. Anyway, I got confused. Sure, Rayleigh is a non-linear function. What about sigmoid?
It is
Very much
clearly
non-linear.
What about 10H?
non-linear as well.
So that what the point I want to make here is all the activation functions which we are choosing are non-linear. We are choosing non-linear function. Okay. So classification type of hidden layer, how to choose a hidden layer activation function. So hidden layer activation function means, you see hidden layer, we always choose say ANN type of, don't go to RNN here. Don't go to the right hand side box. Go to the leftmost, second layer, first graph, multi-layer perceptron. Multi-layer perceptron is nothing but our ANN, which we are studying right now. So in ANN, our hidden layer activation function will always be Rayleigh. Because research has found some results in favor of Rayleigh. Okay. So what those results are, we'll get into that later. We'll get into that later. But research have found that Rayleigh is the very suitable kind of activation function for hidden layers in case of a multi-layer perceptron. Multi-layer perceptron is nothing but our artificial neural network, ANN. And when we go to convolution, then also hidden layer, we choose Rayleigh only. But when we go to RNN, we see CNN and RNN we will discuss later. CNN, the wall to game is different. Now, but I want to tell you a different thing. What about output layer? Output layer, the story is different. Output layer, output layer classification type of problems. Output layer classification of type of binary, I told you we choose sigmoid. Multi-class we choose softmax. Multi-level we choose sigmoid again. And regression type of problem we choose linear activation. Why we choose linear activation? First of all, I want to show you what is linear activation. Linear activation function. Activation function. I want to show you what is it. Linear activation function. So this is a linear activation function. Okay. So this simple equation is nothing but a linear activation function. This is a linear activation function. And I am telling this linear activation function is used in output layer of a regression type of problem. Can anybody tell why? In classification, very clear to us. In classification, for binary classification, we use sigmoid. Multi-class, we use softmax. And multi-level also, we need softmax. Multi-level also, multi-level also, we use sigmoid only. So binary and multi-level, we use sigmoid. And multi-class, we use softmax. Okay, clear. For classification, for regression, I'm telling you, we use this kind of function. Linear, where is that equation? Where is that linear equation? Yeah. Anyway, it has gone somewhere. So we use this equation in linear. So this kind of activation function we use in output layer in case of regression problem. Can anybody tell why? Anyone? In regression kind of problem, we use a straight line equation as our output. Activation function is our output. Why it is so?
Because decision boundary is linear.
There is no decision boundary in regression model. Decision boundary is there only in case of classification problem. Understood? Huh?
No, means like the model can be defined as a linear function.
Yeah, it is because linear regression output is a continuous number. It is a continuous number, right? You are predicting a number which is a continuous number. So continuous number we cannot get with sigmoid, we cannot get with softmax. How can we get a continuous function? Continuous function we can get with the help of a continuous function. So continuous function is nothing but a linear activation function. That's why we use this sigmoid only in this linear function. Now my next question for your homework is note down 2 homework and then we end the class. I think today's is too long class. Sorry for that. So note down 2 homework questions. Malini madam, please note down and then share, please. 3 questions I'm sharing. What is supervised machine learning problem? Number 1 question.
So that was given yesterday. So
Yeah, write down once more. Once more you write down. What is unsupervised class problem? Second question. What is unsupervised machine learning problem? Third question is, what is binary classification? What is binary classification type of problem? Fourth question is, what is multi-class classification? Fifth question is, what is the difference? What is multi-level classification? Multi-class 1 question, multi-level 1 question. What is multi-level classification? And last question is, what is the difference between multi-class classification and multi-level classification? So I want everyone to search Google and find answers to these questions. Malini madam will share the questions with you on the WhatsApp in our Telegram group. So these 6 questions everybody has to submit by next Saturday. Okay, 6 questions given, very simple, half an hour of work for you, but simple question, but you have to do it because I know many of you. If this question, if I ask in the class, many of you will not be able to answer it. That's why I want you to search the Google and do it for yourself. So help yourself. So by next Saturday, submit these questions. So I think that completes our
Sir,
class
one
of ANN.
question